Hi there everyone. In this video we are going to be looking at integration of functions that result in logarithms. Okay, so we're not going to directly integrate the log function, that's a little bit tricky, but we are going to integrate functions that result in logarithms. So it's kind of looking at the reverse, going back from the chain rule that we already know from the last video. One thing I just wanted to point out along with this is the kind of really basic definition of the natural log function. And let's look at this here. We've got the curve 1 over x, and what I'm going to do here is drag this point along here, and we're going to measure the area underneath the curve. So you can see at the moment the area is 0 because we're going from 1 to 1. So we're starting at 1. I'm just going to move this across to 2. So we've calculated the area underneath this curve between 2 and 1, and you can see that's the same as the natural log of 2. This is the basic definition of the natural log function. Okay, it's the area under the curve 1 over x between 5 and 1. So this is just going to be ln 5. This is a really basic definition of what the natural log function is. And you can see on this diagram here, if you draw the area underneath the curve between 1 and whatever it is, and actually draw that function as you go along. So you're starting at 1 there, which is 0, the area is 0, you get this curve here, which is the natural log function. So there's a really basic definition, and you can see that the integral therefore of 1 over x is going to be ln x, and that's our basic definition for this video. If you think of it from the last video where we said the derivative of ln x is 1 over x, then it stands to reason therefore that the integral of 1 over x is ln x plus c. Further extending that, we had the derivative of ln f of x was f dash x over f of x. So now we go back the opposite way. If we integrate functions that look like this, we end up with ln f of x. So it's just going backwards from when we were using the chain rule for doing differentiation of ln f of x. So this is probably the most important one right here. So we're looking for functions that are in this form here, derivative over original function. We know that if we have that format, we know then the answer is going to be ln of the function on the bottom line. So a few examples on doing this and really trying to force functions into looking like derivative over original function. So let's start with this one, the integral of 5 over 2x. I think there's an easy way to do this is just take the 5 over 2 out the front. Remember that you can always take constants out the front of integration before you do it. So that's 5 over 2 times the integral of 1 over x, which we know is ln x plus c. Done, easy. Remember, we're trying to get functions in the form derivative over original. So I really want to force this thing into looking like this. 2x over x squared plus 1. That's what I want it to look like, because then I know that the answer to this one here that I've just written is ln x squared plus 1 plus c. Okay, so the way that I force that is I just put this 5 at the front, and then you can see that this expression here is the same as this expression here. So I've really just forced it into that form by taking the 5 out the front, and then I can do the integration correctly. So my final answer is 5 ln x squared plus 1 plus c. Areas now, we can do areas under curves. This is a really simple one. So the integral from 5 to 2, so the area under the curve, 1 over x between 5 and 2, that is the area. And this is ln x between 5 and 2. So this is ln 5 minus ln 2, which of course we can write as ln 5 over 2 or ln 2.5. That's the exact area underneath the curve. It's worth noting in this question here that if we want, let's say, the area between -2 and -1. Okay, so here's the curve y equals 1 over x, and I want that area there between -2 and -1. You can see we run into problems if we just use this formula here. So if we say the area is between -1 and -2 of 1 over x dx. That looks perfectly fine. But ln x between -1 and -2, I'm sure you can see that we've got a problem here. ln -1 minus ln -2. Okay, we know that the logarithm function is only defined for positive x values, so this is no good. This will not work. ln of -1 and ln of -2 just doesn't work. So there's a way that we overcome that, and let me show you how that works. What we do is we just say, well, isn't that the same as the area between 1 and 2 under this curve here? And in fact it is. So rather than changing the limits of the integration, what we do is we say more generally that the integral of 1 over x dx is ln modulus of x plus c. Okay, and that modulus there just takes care of any negative x values that we might be substituting into the formula. This is particularly important if you're doing definite integration here, where you're finding the area under the curve. Okay, so those absolute value signs just mean that if it's a negative, make it a positive. So if we went back to this example here, we'd have the modulus signs here. So this would just be ln1 minus ln2, 0 minus ln2. So you would get a negative number, which is correct because the area is below the curve. So you get a negative number, but of course you just make that positive. The question said, what's the area under the curve between -2 and -1? Okay, first one here, the integral of 6 over 3x plus 1. Again, I'm just going to do the same thing. I'm going to force this into the form that I want. The derivative of 3x plus 1 is 3. So that is what I want, so that I can say the answer is ln of the bottom line. So by putting a 2 out the front, you can see I haven't changed anything. I've just written it in the form that I want it there. So the answer is 2 ln, and I'm going to include the modulus signs there, 3x plus 1 plus c. For part B, exact same thing. What I want is the derivative of cos 2x on the top line. And these are hard to recognize at the start, but once you get going, you'll be fine. You'll recognize them. So the derivative of cos 2x is negative sine 2x times 2. So negative 2 sine 2x. That is what we want. And you can see I've nearly got that on the top line. I've got 8 sine 2x. So a negative 4 out the front. You can see now that what I've written is exactly the same as the question. So the answer is negative 4 ln cos 2x plus c. And I'd encourage you to write the modulus signs now. Even though this is an indefinite integral, if you have to start substituting in a definite integral situation to work out the area, it's good to have the modulus signs. So here's another integral that we could include now, the integral of tan x. Okay, which looks like, how the heck would you do that? So tan of x is sine x over cos x. So it's really similar to the last one I did. What we want is in this form here, right? Yep, we want it in the form derivative over original. So with that negative at the front there, that takes care so that now it's exactly the same. So now it's in the form derivative over original, negative ln cos x plus c. So there you go. The integral of tan of x involves a natural logarithm function. Who'd have thought that? That's it.